Now let's see the hybridization. Hybridization concept which was explained, which was introduced only to answer the certain queries related to the molecules geometry. Hybridization is considered as a hypothetical concept. It's a hypothetical concept, and this concept is used for those molecules where we cannot explain the things by using a valence bond theory. So whenever the hybridization concept comes, so first we have to answer that why we are using a hybridization concept, because as I said, this concept can be used only if I cannot explain the geometry of a molecule or the certain things by using some other theories like valence bond theory, right? So what is hybridization? Hybridization is nothing but the mixing and recasting of the atomic orbitals of the same atom of approximately same energy and different shape, and forming some new molecule, forming some new orbitals with the same geometry, same shape, and same energy. As I said, it's a mixing and recasting of atomic orbitals of same atom. The very important thing that in this case, whatever the atomic orbitals are there, those atomic orbitals are of same atom. Okay, then these atomic orbitals should have the atomic orbital before mixing. Before mixing, they should have different shape and approx same energy. So it's a mixing and recasting of atomic orbitals of same atom having a different shape and approximately same energy to produce equal number of new orbital of having same energy and same shape. Okay, so this I can say that this is the definition of the hybridization, that it is a mixing and recasting of the atomic orbitals of the same atom having a different shape and approximately same energy to produce equal number of new orbital having a same energy and same shape and properly oriented in a direction. Now what is hybridization in simple word? See, hybridization is nothing but the preparation of an atom, the atomic orbital of an atom before the bonding. Means it's not about the bonding, during the bonding. This process doesn't take place during the bonding, but it is a process which happens before the bonding. Suppose, for example, I can say, suppose if there is a war, then in case of war, the things which is before the war we do some preparation. So similarly here, hybridization, I can say that it's nothing but the preparation before the bonding. Means when the atoms moves for the bonding or when atoms comes for the overlapping, then before the overlapping it's carried out certain changes in itself, and that is called as, and that change is a hybridization here. Now here, as I said, it is a mixing and recasting of atomic orbital of same atom. That means here the atomic orbital which undergoes mixing, and so first the atomic orbitals, whatever the atomic orbitals we are having for the given central atom. Here the hybridization generally takes place in a molecule. Generally the central atoms undergoes hybridization process. That is, atomic orbitals of central atom undergoes hybridization process. So atomic orbitals of the central atom undergoes mixing and recasting process and produces some new orbital. How many new orbitals are produced? I can say that they produces equal number of new orbitals having a same energy and same shape. For example, I can say, suppose I have 5 shapes of, suppose I have a clay, and we have 5 shapes of a clay, 5 different shapes of a clay, right? And they have a different size also. Here I am relating the size with the energy. So I can say that we have clay, 5 different shapes of a clay, and they have the different shape and the different energy. So we just mix all the clays, all the shapes are mixed, and after mixing I'm again making some new shapes, producing some new shapes, and now the shapes which has been produced is exactly same. All the shapes are exactly same, and all are having the same energy. Having a same energy, it means all are having all the shapes which are produced now, they all are having a same size. It means they have a same energy. And how many new shapes has been produced? Equal to the number of the shapes which are mixed. So how many shapes were mixed? I said we are mixing 5 shapes of a clay. So now we are producing 5 new shapes. So as I give the example for the shape, the clay, similarly we are having for the orbitals. Here the old orbitals undergoes mixing process and then recasting. Recasting means some new orbitals are formed. How many new orbital? Then equal to the orbitals which mix. Suppose if there is 3 orbitals are undergoing mixing process, 3 new will form. If 4 are undergoing, 4 new will form. And then after that, all the new orbitals which are forming, they are called as hybrid orbital, and those hybrid orbitals are having the same shape and same geometry. Okay. Now let's see the steps which are involved in a hybridization. The step number 1 which is involved in hybridization is the excited state, formation of excited state. Formation of excited state. This state is written only if the number of half-filled orbital and the number of valency of an atom does not matches. This step is written only when the number of half-filled orbital and the valency of the atom does not match. It means the number of half-filled orbital and the number of bond formed by an atom is different. The example, I can say the carbon whose atomic number is 6. Its electronic configuration, I can say 1s2, 2s2, 2p2. Here in case of carbon, we have 2s2 and 2p2 configuration. How many half-filled orbital? 2, but we all know that number of bond formed by carbon is 4. That means carbon valency is 4. So now, according to valence bond theory, the carbon will form on 4 bonds only if it is having a 4 half-filled orbital. But here the half-filled orbital is 2, so now I want there should be a 4 half-filled orbital. So as I said while talking about the valence bond theory limitation, I said if the carbon is having a 2 half-filled orbital, then how it is forming a 4 bond? And if it is forming a 4 bond in a nature, it means it is having a 4 half-filled orbital. So how all these things happens? So here what happened, this is a ground state of carbon atom. Now carbon undergoes excited state. What happens in case of excited state? In excited state, the electron from the completely filled orbital jump to orbital which is empty. It always jump to empty orbital. So electron from this will jump to this, and it will be called excited state now. So the configuration will changes to 1s2, 2s1 and 2p3. So now this will be s1 and this is p3. 3 half-filled orbital now we have. Okay. So now how many half-filled orbitals in total we have? So total half-filled orbitals are 4. So since total half-filled orbitals are 4, so simply now I can say that the carbon will form 4 bond. Now if the carbon, now again during the bonding, the carbon doesn't use its s and p orbital for the bonding separately. Because if the carbon uses its p orbital, then all the angles is going to be 90 degree, as I said in the case of ammonia and water according to valence bond theory. So here what happened, now the carbon undergoes preparation, some changes before the bonding. What changes it carries out? Whatever the orbitals we are having in the carbon, that is half-filled orbital, they all undergoes mixing and recasting process. All the orbital which are present in a valence shell, they undergoes mixing and recasting process. How many valence orbital we are having? Valence shell orbital 1, 2, 3 and 4. So 4 orbital undergoes mixing and recasting process, and hence 4 new orbitals will form. So 4 new orbitals, let's see. From here we have one s orbital and we have 3 p orbitals. So s is a spherical in shape and the p is that same dumbbell shape. All lobes are equal in size. So these 4, 1 s orbital, and here we have 3 p orbital. They undergoes mixing and recasting process, and how many new will form? If 4 are undergoing mixing and recasting, then 4 new orbital will form. Here you can say that the shapes are different. Shapes are different, but the 4 new orbitals which are forming, they have same shape. These are the 4 orbitals, 4 new orbitals. Each lobes have the opposite lobe also, but it has already reduced in a small size like this. This here, for this also we have a small lobe, and here also we have. Now these lobes are already in a smaller size for the maximum overlapping of on the overlapping side, means all the energy of the opposite lobes also get concentrated on the overlapping side, so that maximum overlapping should take place and the bond form should be strong bond. So each of them, now this was s orbital, this was p orbital. Now each of them is called as sp3 hybrid orbital. Now these are called hybrid orbital. That is orbital which are formed from the hybridization. So whatever the electron was present, here the electron was present in s orbital in case of px, py and pz. Now these orbitals will move to these 4 orbital. So these are the 4 orbital. Now the carbon is having s and p orbitals, but during the bonding, instead of carbon and this s and p orbital, what the carbon did, the carbon just mix its old orbital and form a new orbital. So from the carbon, for the bonding, now this new hybrid orbital will move. Means if I am talking about the formation of ammonia, then from the carbon side who will come for the overlapping, then from the carbon side these sp3 orbitals will come. Why I said it is sp3 orbitals? The name of these hybrid orbitals depends upon the name of orbitals which undergoes mixing and recasting process. As I said, one s orbital, and how many p orbitals are undergoing? 3, and that's why the name is sp3. Then we have sp2 orbitals. What is sp2? The name itself says that one s orbital and the 2p orbital undergoes mixing and recasting process. Similarly, we are having sp. Similarly, we have sp3d, sp3d2, sp3d3, etc. So this is how the hybridization occurs. And now in the case of the new 4 orbital, the 4 orbitals which has been formed, they all are having electrons, so they all overlap each other, so they all repel each other. So to minimize the repulsion, these all 4 orbitals are present far away from each other. They all are present far away from each other. It is nothing but nothing but I can say that is this geometry is called as a tetrahedral geometry. Okay, so this is formation of excited state. All the 4 new orbitals which has been formed, they were having s-n orbital and p orbital. Simply I can say they have the different energy, but these 4 orbitals which has been formed, they are having equal energy. All are having same energy. They all are having a same shape also. They all are oriented in such a way that the repulsion between them should be minimum, and here the repulsion distance or the angle between the orbital is 109 degree 28 minutes. That is in case of tetrahedral, it is 109 degree 28 minutes. So this is about the hybridization. We will learn about the different types of hybridization. Okay, now before starting the examples of the different types of hybridization, let's see the different types of a covalent bond which we are having, because again here we require the understanding of the covalent bondings. We have 2 types of covalent bond. The one is called as a sigma bond, as we all know, and the second we have pi bond. Now, what is sigma bond and pi bond? Simply, sigma bond, these are the bonds which are formed due to the axial overlapping of the orbital. So this is formed after the axial overlapping of the orbital, while this is formed the lateral overlapping, due to the lateral overlapping. When the two orbitals, now see every orbital have an axis. For the s orbital, I can say s orbital being a spherical in shape, so all are going to be axis. You draw a line any direction, all are going to be axis only in any direction, right? But for the p orbital here, I can say for this px, this is the axis. For py, this is the axis. For pz, this is the axis. So when two orbitals overlap on axis, the bond form is called as a axial overlapping, and the bond form is called as a sigma bond. But when the same two orbitals are overlapping laterally, then it is called as a pi bond. Now in case of sigma bond example, I can say whenever two s orbital overlap, this is the first s orbital, this is the second s orbital. As I said, in case of s orbital, whenever it overlap, the bond is going to be sigma bond. Now let's see, this is overlapping. So here I can say this is the axis of this orbital, this is the axis of this orbital. So ultimately the overlapping taking place on the axis. So whenever s orbitals overlap, it is a sigma bond. Similarly, an s orbital, a p orbital. S orbital, and this is p orbital. This is the axis of this p orbital. Now the overlapping will be, and here the s orbital is overlapping. Again, whenever a s orbital and p orbital overlap, the bond form is always sigma bond. Means out of two orbitals which are overlapping, if any orbital is a s orbital, the other orbital should be anything. But if the one of the orbital out of two, one of the orbital is a s orbital, the bond is fixed, that is, it is going to be a sigma bond. Now if two p orbitals are overlapping, like this is the first p orbital, second p orbital. Now the possibility is like whether they are overlapping on axis or not. This is the axis for this p orbital, this is the axis for this p orbital. Now they are overlapping. Say the overlap. So here I can say the axis was this. Overlapping occurs on axis, and since the overlapping occur on axis, that's why the bond form is nothing but the sigma bond. Now lateral overlapping. What is lateral overlapping? Let's see. This is a p orbital. As I said, pi bond, that is lateral overlapping, is not done by the s orbital. S orbital always form axial overlapping. This is the first p orbital. This is the second p orbital. Axis for this and axis for this. Now let both are overlapping. Now how they will overlap? Then simply I will say first orbital, and they will overlap laterally. They are overlapping on axis, they will overlap laterally. And when they overlap laterally, I can say the overlapping takes place on the upper region as well as on the lower region. So here whether the overlapping is on axis or not, then answer is no, because this was the axis for this, and this was the axis for this, and here the overlapping region is this one, which is not on the axis. So this is a lateral overlapping. Now in case of sigma, that is when the two orbitals overlap on axis, then I can say that between the nucleus, the number of electron increases. Here the overlapping, that means the number of electron increases, and if the number of electron increases, then ultimately the repulsion between the nucleus decreases. And if the nucleus repulsion decreases, it means the attraction becomes stronger and stronger. And the second thing, that when the orbitals overlap on axis, then ultimately on axis the overlapping strength, the extent of overlapping is always very high, and that's why the bond form is always strong bond, because according to valence bond theory, the bond form and the strength of a bond depends upon the extent of overlapping. And why we are saying that here the extent of overlapping is more, the reason because the nucleus repulsion has been reduced due to the presence of these electrons. Now when the orbitals overlap on laterally, what happens when the orbital overlap laterally? Where the electron cloud will increase. The electron cloud will increase in the overlapping region, that means in this region. So here the electron is increasing, due to which I can say that the nucleus repulsion doesn't reduced. Here the nucleus repulsion reduces due to this electron, which doesn't happen in this case, and that's why the attraction is not very strong, and I can say that the bond is not too strong as the sigma bond. Since here the overlapping takes place on axis, so here the rotation of atom is possible. Like the atoms can be rotated on the if the bond is a sigma bond, well, in this case, such type of rotation is not possible because the bonds are not forming on axis. Here, it's a lateral overlapping. This bond is formed by the s orbital. If there is a s orbital, always forms sigma. This is also formed by p orbital. And the very important that this bond is formed by the hybrid orbital. This, it is formed by p orbital. This is also formed by d orbital. This is formed by p orbital, d orbital, and unhybrid orbital. S orbital doesn't comes into the picture. Hybrid orbitals, whenever an hybrid orbital will overlap, it will always form a sigma bond, will not form pi bond. What is hybrid orbital? This is hybrid orbital. That is orbital. So if all four are hybrid, they will always form a sigma. Whatever will be the condition, they will form a sigma bond only, because the hybrid orbital always forms sigma bond. So if in any molecule, if there is a pi bond formation has been present, then keep in mind that you have to make such an arrangement that there should be some unhybrid orbital, so that we can explain the pi bonding in a molecule if there is a pi bond. So this is about the hybridization and the sigma and pi bond. The sigma bond, just keep in mind, if two orbitals are overlapping on axis, the bond is going to be sigma. Here in the next part, we are going to learn about more and more about the hybridization. So whenever it is a hybrid orbital, bond is sigma, and if it is an unhybrid orbital, then the bond is going to be pi bond. Now let's see some hybridization, the different types of the hybridization which we are having in a syllabus. So the first one is a sp3 hybridization. As the name says that, what happens in case of sp3 hybridization? Then I can say that this is the hybridization in which 1s and 3p orbitals. So as I said, 1s and 3p orbitals undergoes mixing and recasting process and produces how many new orbitals? 4 new orbitals. How many orbitals are taken part in a hybridization? I can simply say 1 plus 3, that is 4. So 4 new orbitals will form, and those 4 new orbitals will be called as hybrid orbitals. And those 4 new orbitals will have a same energy, same orientation, and same energy, same shape, and they will be properly oriented in a space so that the repulsion between them should be minimum. So sp3 hybridization, as the name says that 1s and 3p orbital undergoes mixing and recasting process. So 1s and 3p. So this is 1s orbital plus 3p orbitals. 3p orbitals means px, py, and pz. All three will take part. Px. The second one, and this is the third one. All three are taking part. And so this is going to be px, this is going to be py, and this is going to be pz. So 3p orbitals and 1s orbital. They are undergoing mixing and recasting process and produces 4 new orbitals. So that 4 new orbitals will be this one. All are having a same size, same shape. Of the opposite sides are all smaller in size. Okay, so these are the 4 sp3 orbitals. This is the axis for this, this is the axis for this, this is the axis for this, and this is the axis for this. sp3 orbital, each of them are called sp3 hybrid orbitals. And the geometry is called as tetrahedral geometry. This is called tetrahedral geometry of sp3 orbitals. Now, how they are, suppose if I am talking about the geometry, then geometry is something like this. So these are the 4 orbitals that I am joining all 4. So when all 4 are joined, then geometry which is formed is called as, so when all 4 are joined, then it is called as tetrahedral geometry. And here, these lines are nothing but the sp3 orbit, the orientation of these orbitals. So here the angle between these 2 orbitals, that means these two, or these two, is fixed, that is 109 degree 28 minutes. This angle is fixed, 109 degree 28 minutes. And this geometry is called as a tetrahedral geometry. So whenever an atom undergoes sp3 hybridization, that means the orbital of that atom will be of like this, and the geometry it will have sp3 hybrid. It will have a tetrahedral geometry. Now this orbital, let's see the same thing with the help of animation, that how it looks. So in the animation you can see that there are the 4 orbitals. These 3 orbitals are on the bottom side, and this is like this. I can say these 4 orbitals are present like a stand of a mic. I can simply say that like a mic, stand of a mic, that means 3 are here and the 1 is on the top. The same thing here you can see in the animation also, that is there are the 4 orbitals. Each orbitals are having a same shape. They all properly oriented, that means at the same distance from all the sides. And here in that case I can say the angle between the 2 orbitals are, that is angle between the 2 lobes are always same, that is 109 degree 28 minutes. All orbitals are producing a same repulsion from each other. So this is about the sp3 hybridization. The second type, the example for sp3 hybridization, some examples like methane undergoes sp3 hybridization, water undergoes sp3 hybridization, ammonia undergoes sp3 hybridization, all alkanes, all the carbon atoms which form a single bond, that is all 4 single bond, that is in alkane all the carbon undergoes sp3 hybridization. After sp3 hybridization, the next is sp2 hybridization, the second one. As the name says that sp2 hybridization, that is 1s orbital and 2p orbital. That 2p orbital is generally px and py orbital, undergoes mixing and recasting process, and they produces 3 sp2 hybrid orbital because 3 are overlapping. So 3 sp2 hybrid orbitals are formed. Let's see how it happens. 1s orbitals and 3p orbitals. 2p orbital. So 2p, that is, it is going to be xy. Now here this is your px and this is py. As I said, you can say px, py, pz or px, py, pz, something like that. So z-axis is not considered. There is only 2 orbital, px and py orbital. Now they undergoes mixing and recasting process. And after mixing and recasting process, how many orbitals? 2, 3 are mixed. So 3 new orbitals will form. And those 3 new orbitals are something like this. First one. Those 3 orbitals are, I can say, they are oriented on the 3 sides of 3 corners of the equilateral triangle. So this opposite side of this, opposite side of this. If I am joining all 3, and if I am joining these 3, you will get an equilateral triangle, and being an equilateral triangle, this angle is going to be 120 degree because the central atom for that particular triangle. So this is called trigon. This is each of them is called as sp2, sp2 and sp2 hybrid orbitals. And the bond angle between each orbital is 120 degree. And the geometry, as I said, it is trigonal geometry. So sp2 is something like this. As I said, this angle is 120 degree. This angle is also 120. This angle is also 120 degree. And I said it's a trigonal plan. This is called trigonal planar. This is called trigonal planar geometry because all the 3 orbitals present on a same plane. That means it comes on a 2-dimensional figure. This here in an animation saw that all 4 orbitals cannot come to the same plane. But in the case of this, all 3 orbitals are present in the same plane, and that's why the name is given trigonal planar geometry. Trigonal planar. So this is about the sp2 hybrid or hybridization. See, this is the animation of the sp2 hybridization, in which you can see that the 1s orbital, the 1 orbital is present here, the second is here, and the third is here. So, and all 3 orbitals are, means if I'm going to join the if I'll join these 3 points in a animation, you will get a equilateral triangle, and here the angle between the all orbitals is nothing but the 120 and 120 degree. You can see that in our animation that all the three orbitals can easily accumulate on the plane on this, it is all three are getting accumulated on, or they all are lying in the single plane, that is they are lying on a board. That's why they are called as a planar, that is a trigonal planar geometry. Then the third one, the third type which we are having is SP hybridization. SP hybridization is also known as a linear hybridization. So if there is a question like linear hybridization, then keep in mind it's nothing but the SP hybridization. Now what happens in case of SP hybridization? One s orbital and the one p orbital undergoes mixing and recasting process and produces two new hybrid orbitals. Each of them is called as SP hybrid orbitals, right? Having a same symmetry and same energy. So in the case of this, 1s and 1p orbitals are undergoing mixing and recasting. So 1s orbital plus 1p orbital, only 1p orbital. This is px, py and pz. So only px is undergoing. So two new orbitals you will get. This is the first new orbital, is the opposite side. The second orbital is the opposite side. So this is the axis for this orbital, this is the axis for this orbital, and here you can see that angle is going to be 120 degree, and that's why it is called as linear hybridization, because the geometry is linear. 180 degree, that is linear geometry. Now here in this diagram, don't think like it appears like the dumbbell shape, then where the circle is, where that sphere is. See, I can say that it's not these four orbitals which has been formed, it's not like this also, this one. It's a result of the mixing of these four. Means these four, like I said in case of clay, if you are mixing the clay, all the shapes will get destroyed. And we are making a new shapes, and that new shape will be totally different. So we cannot, here I'm not going to search that where that s orbital is present in this case, because that s orbital has mixed and they had formed this one. Similarly, you don't think like here this and this is same. They are different. This is only a orbital and this is hybrid orbital. This is formed by the mixing of both. Both mixes with each other and they form a new orbital. And these two contains, in this the s is also present as well as the p is also present, and each of them is called as sp hybrid orbital. Same thing you can, now the geometry of this, you can the orbitals you can see in animation also, that here the two orbitals which are the first orbital and the second orbital, and you can see that the angle between them is 180 degree, and that's why it is called as a linear hybridization. So we have total three hybridization: the sp3 hybridization, sp2 hybridization and sp hybridization. In case of sp2 hybridization, here sp3 hybridization, we have a tetrahedral geometry. All four orbitals are oriented at the corners of the tetrahedron, regular tetrahedron, and as I said, it's like a stand, mic stand. And then second is the sp2 hybridization, where we have trigonal planar geometry. Three sp2 orbitals, the angle between them is 120 degree. For sp2 hybridization, the examples we have alkenes, all the carbon which form double bond. Then we have the example like BF3 molecules. sp hybridization, all the carbon which form triple bonds. That is in case of alkyne, we had learned in 11th standard. In alkyne part, that is that the carbon is forming there is a carbon-carbon triple bond, and this carbon, each carbon undergoes sp hybridization. Here each carbon undergoes sp2 hybridization. And linear geometry, that is hybridization itself, called as a linear hybridization. So now let's see. So as I said, these are the preparations. This hybridization is nothing but the preparation of the central atom before the bonding. Now let's see the one-on-one examples of all the hybridization, how this hybridization takes place, how the molecules or the geometry is formed.